Welcome back. I've got another lecture for you regarding leveling. This one is fairly short and pertains primarily to not only three-wire leveling, but benchmark circuit corrections and survey planning. What I have here for you is a partial excerpt from some real-world survey notes that were done showing three-wire level notes. And I want to point out some things regarding how these notes work. This will lay the groundwork for some of the computations we do with benchmark circuit corrections. I want you to notice that in these level notes we're set up very much like the basic notes that you've already worked with. We have 5 columns: station, backsite, height of instrument, foresight, and elevation. But for every reading, whether it's a backside or foresight, we're actually taking 3 readings. For instance, the backside on the first benchmark at benchmark 9904, the 3 readings are 2.90, 2.29, and 1.68. Those are on the upper stadia hair, the center horizontal crosshair, and the lower stadia hair, respectively. We use all 3 readings and we will average the 3. Just below the third reading you can see an average that is listed there, expressed to 3 places. In this case it's 2.290. Before we'll accept the 3 readings, every time we make those 3 readings we must compare the interval between the upper hair and the center hair with the interval between the center hair and the lower hair. The difference between the upper and middle hair on this first reading we've mentioned so far appears to be 0.61 feet. Well, if I compare that to the interval between the center and the lower hair, it also works out to 0.61 feet. The upper interval and the lower interval should agree within 1/100th of a foot. If you have more than 1/100th of a difference, then you need to reread all 3 of the hairs, the upper, the middle, and the lower hairs. And if you have a changed reading, simply line through the erroneous reading and write the corrected reading next to that. At each site we have the upper, middle, and lower hair readings, and we can record the average as we go. Or you can record that average after the fact. Leave room for that average reading, and then leave room for a distance. The distance can be computed after the fact, but how do we get that distance? We simply subtract the lower hair reading from the upper hair reading and multiply that difference by 100. So you can see that 2.90 minus 1.68 is a difference of 1.22. 1.22 times 100 gives us a distance of 122 feet. This distance measurement method is fairly crude, and it is not accurate to more than a foot or 2. So I would not use it for anything other than distance estimation. Notice now that since we are using averages computed to 3 places, we're going to carry our elevations and HIs to 3 places. As you can see at the HI that is in the turning point 1 row, we have expressed it to 3 places, and the backsite that was used to compute that HI, the average of 3.127, is, I guess you could say, defined more finely than the smallest increment on the rod. When we average these 3 readings, 4.04, 3.13, and 2.21, then the result of 3.127 will be the reading that we use to compute the HI. Likewise for the foresights, you'll see that we can express those to 3 places, and use that as the basis for our calculations. The average, as you can see, shows here, and we use it to compute this HI, and then the distances you can see shown for each of our sites, back sites and fore sites. These distances will become useful for determining not only the total length of the circuit, but the length of each shot. You can use them to see how well you are balancing these shots. The fore sight taken on turning point 1 and the back sight on benchmark 9904 were both taken from the same setup. You can see one was 122 feet and that fore sight was 180 feet. Not bad for a balance. It works out okay. Likewise, at the next setup, back sighting at turning point 1 and fore sighting at turning point 2 is even better, 183 feet versus 200 feet. This shows you how well you're balancing and thus can alert you to places where you may have errors if you do have an imbalance later on. What I want to present to you here is now how we would correct our closure error in a level circuit. Consider that on the left we have a benchmark that we'll call benchmark start, and we're determining the elevation of two other benchmarks. We'll call them benchmark new 1 and benchmark new 2. Well, we've run our circuit through these. In fact, it's a loop circuit. We started and ended at benchmark start, and its known elevation is 916.15. Well, our computed elevation came in at 916.06. In this case, because of the length of their circuit, I can tell you that the allowable error exceeded the actual, so this 600th error is acceptable. One of the things that we can get from our 3-wire leveling methods is the distance from benchmark start to benchmark new 1, and from new 1 to new 2, and from new 2 back to start. So those distances are 5,470 feet, 3,020 feet, and then 1,350 feet in sequence. And those total to 9,840 feet. That is our circuit length. One of the 3 methods mentioned in the last lecture for distributing the error in a level circuit like this is to distribute it based on the distance, the cumulative distance through the circuit for each benchmark. So we're going to adjust the elevations at benchmark new 1 and benchmark new 2, because if there is error at our closure point, there is necessarily some portion of that error that is as present at new 2 and at new 1. Our closure error is 6/100ths of a foot. In fact, it's a negative value. That is, we came in lower than the published elevation. Well, if our error is negative, then we must apply a positive correction at the final location in order to adjust that location. We're not going to simply say we have 2 elevations there. We're going to make sure that our adjusted elevation agrees with the original. If we have a negative error and a positive correction there, then we're going to have a positive correction at the other 2 benchmarks as well. That correction will be based on the distance to the first benchmark expressed as a fraction of the total. So here we can see that the correction is 5,470 feet divided by 9,840 feet. That fraction times the total correction for the circuit is really going to give us a correction for this benchmark of 0.033 feet. My adjusted elevation becomes our calculated elevation plus this correction. So that works out to be, if I round back to the nearest hundredth, 861.57 feet. Well, that's fairly straightforward for the first benchmark. The second benchmark is computed the same way, and the distance is the total distance from the starting bench to this second benchmark. So 5,470 got us to the first benchmark plus an additional 3,020 gives us a total of 8,490 feet to the second benchmark. Well, that 8,490 feet is a fraction of the total. So we take that fraction times the total correction in the circuit, 6/100ths of a foot, and that gives us 0.057 feet. When I apply that to my calculated elevation, then I get an elevation rounded to 2/100ths of 885.69 for that benchmark. So this is a very straightforward and simple example of how we use the cumulative distance from the beginning of the circuit as a fraction of the total circuit length times the circuit correction to get the correction at any particular benchmark. I want to give you an example then of how we go about planning small or even large level circuits. This example is how we actually established the control elevations on a network of control monuments here on the Parkland campus over 10 years ago. At the upper right of the screen, you can see a red triangle labeled LC0143. At that location is a first order class 2 benchmark that is set in concrete on a railroad bridge crossing a stream. This is just south of the Champaign Post Office on Mattis Avenue. Our intent in this particular survey was to hold that elevation as our control to establish the elevations of new monuments on the Parkland campus. You can see those 7 monuments denoted with yellow triangles. Rather than run one long circuit, which in this case would be about 3 miles all in one shot, rather than run one long circuit and risk having blown measurements in that circuit and have to redo the whole thing, broke it down into 2 phases. So the first phase was a simple loop circuit. And in this circuit, we started at LC0143 and ran to the northeasternmost benchmark, then to the north central one, then to the northwestern bench, and then returned on the same path. Across each benchmark, we turned, or we can say we used each benchmark as a turning point. There were additional turning points between the benchmarks as well. Ultimately, we closed back to LC0143. Now, this loop was only about 3/4 of a mile each direction, so a total of 1.5 miles. Once we determined that closure was good here, acceptable within the limits of third order accuracy, then we computed those elevations and adjusted them. So the adjusted elevations, now denoted in red, became the basis for the next phase. In the next phase, we ran a connecting circuit from the northwesternmost monument down to the southwesternmost monument, and then continued counterclockwise around the remainder of the loop, as you see here, back to our northeasternmost monument. By running this circuit in 2 phases, the first phase gave us a total loop length of about 1.5 miles. And then the connecting circuit is also about 1.5 miles long. By giving ourselves a closure check at the end of each phase, we were effectively taking less risk and increasing our confidence at intermediate points in the survey. If I back up, I think you can understand that in our loop circuit, if I'm calculating as I go, then I can determine when I revisit the second benchmark on the return run, and when I revisit the first benchmark on the return run, I should get the same elevation going back as I did coming out. Those are ways that we can check our work as we go. Likewise, we could mark the turning points temporarily and leave those temporary markings in place and use those same turning points on the return leg. This gives us internal checks and increases our confidence in the field as we go. On this connecting circuit, I really had no such checks until I got to the end, because I was not retracing any of my steps. This classic case of using two different types of circuits worked very well for us, minimized risk, and made our survey much more efficient should we have to rerun any portion of it. We were successful in the first try and did not have to do any reruns. You may find this information useful on large-scale projects or small-scale projects, but no matter the size, you will find that building checks into your process will help you gain confidence and help you identify errors perhaps as they occur or shortly after they occur, thus making your correction efforts efficient and quick.